When we want to solve a system of linear first-order differential equations, the first thing we need to do is determine if the system is homogeneous or non-homogeneous. If the system is non-homogeneous, there's three basic cases that the solution could fall into. So let's take a look at those. We know that the solution to a homogeneous system needs to look like a constant times some solution vector plus another constant times some solution vector and so on. But the question is, what are those constants and what do solution vectors look like? How do we find them? So this theorem that we have, the general solution to homogeneous systems, is going to help us out with that a little bit. So when we have lambda 1, lambda 2 up to lambda n, those are representing n distinct real eigenvalues of the coefficient matrix A of a homogeneous system. And k1, k2 up to kn are going to be the corresponding eigenvectors. So each of those eigenvalues gets an eigenvector that goes with it. Then, using those things, the general solution on an interval from negative infinity to infinity is given by x equals c1 k1 e to the lambda 1t plus c2 k2 e to the lambda 2t and so on up to cn kn e to the lambda nt. You might not know what an eigenvalue is, you might not know what an eigenvector is, and so we're going to take a look at an example where we're going to find two distinct eigenvalues and then we'll find their eigenvectors. And then we'll be able to use this theorem. So we need to first find the eigenvalues. So let's talk about how we can do that. So to find eigenvalues, we're going to start off by using something called a characteristic equation. So what we're going to be doing is we're going to be taking the determinant of our A matrix minus lambda times an I matrix. Now, our A matrix, remember, is our coefficient matrix. So this is going to be the determinant of our A matrix is going to be 2, 3, 2, 1. Those are our coefficients on our differential equations. And then minus lambda times I stands for the identity function, where there's a 1 on everything down the main diagonal, what it's called, going top left to bottom right. And then there's zeros everywhere else. So the 2 by 2 identity matrix that we need since A is 2 by 2 looks like 1, 0, 0, 1. So to multiply lambda times the identity matrix, we're going to be taking the determinant of 2, 3, 2, 1 minus, we'll have lambda times 1, so lambda in the top left position, lambda times 0, so 0, lambda times 0, lambda times 1, so lambda. And then we'll, of course, be subtracting those two matrices, and I'm going to rewrite it now with the vertical bars denoting that we're going to be taking the determinant. So we'll have 2 minus lambda in the top left position. We'll have 3 minus 0 in the top right. We'll have 2 minus 0 in the bottom left. And we'll have 1 minus lambda in the bottom right. And that's the determinant we're going to be taking. So taking that determinant, then I get 2 minus lambda times 1 minus lambda minus 3 times 2. And when I multiply this out, I'm going to get lambda squared minus 3 lambda minus 4 after I multiply it out and combine like terms and rearrange it a little bit. And we're going to look at that, and we're interested in when this determinant is equal to 0. So if we want to know when this is equal to 0, I have a quadratic function here set equal to 0. So factoring is probably a way to go, or you could use the quadratic formula. Choose your own adventure here. So I'm going to factor it, and we'll find that we have lambda plus 1 and lambda minus 4 equals 0. So we'll set both of those equal to 0 and solve. So this is going to tell us that lambda 1, my first value that I could get for lambda, is negative 1. And lambda 2, the second value I could get for lambda, is 4. It doesn't matter which one you decide is lambda 1 and lambda 2, but it's a really good idea to start labeling them at this point in time. So the thing that's super special about eigenvectors is that if you take a matrix and you multiply it times an eigenvector, it results in the same thing as multiplying that eigenvector by a constant. And the constant that it's the same as multiplying by, that's your eigenvalue. And so doing that, we know then that if we take our A matrix and multiply it times our eigenvector, I'm going to say this one's K1 because we're going to use our lambda 1 here. That's the same as saying, you know what, I'm going to take lambda 1, so 1, and multiply it times the eigenvector. I can then use that I know what A is, and I know my lambda value. I've already plugged in my eigenvalue, and I can solve for K1. So A was my 2, 3, 2, 1 matrix, and my eigenvector, I don't know what it is, but I know that it has entries, 2 entries in it. So it's K1 and K2. And I know it's going to end up equaling negative 1 times that same eigenvector of negative, or K1, K2. Now my goal here is to find out what are K1 and K2. So I'm going to multiply my matrix times my vector. To do that, I'll be going across the rows of my matrix and down the column of my vector, multiplying. So I'll do 2 times K1 plus 3 times K2. And that's going to be my top entry since it was the top row of my matrix that I was multiplying by. Now I'm going to use the second row of the matrix to multiply, and I'm still going to be multiplying down the vector, and it's going to give me my second row of the vector that's my solution to this. So I'll have 2 times K1, and then I'll be taking 1 times K2, so plus 1 K2. And this is going to equal multiplying negative 1 times K1, K2 gives me negative 1 K1 and negative 1 K2. Now you might notice at this point I actually have 2 equations being set up, because if these 2 vectors are equal to each other, that means that the top and the bottom of them must be the same. So this is really 2K1 plus 3K2. That's the top of my vector on the left. It must equal the top of my vector on the right, so that has to equal negative K1. And I know that my bottom 2 entries have to be equal to each other, so 2K1 plus 1K2 must equal negative K2. And I can combine like terms. This is a system of equations now with two unknowns. Two equations, two unknowns. So I know I can solve for K1 and K2. And when I do that, I'm going to find that K1 is going to equal negative K2. Now, when you're solving for the entries in eigenvectors, this is a really common occurrence. In fact, it should happen this way. You'll get some relationship between the two entries instead of particular values. That's because vectors are determined, they're giving you a direction. And this relationship between the two entries is describing a direction. The actual length of the vector, it could be any length and it will still behave in the same way as an eigenvector. What that means is it means you get to choose a value for one of the entries and then solve for the value of the second entry. 0 is off limits for choosing, but anything else is. So I'm a big fan of choosing 1. So I'll use K1 equals 1, which will mean that K2 must equal negative 1. So this all means that capital K1 is going to equal 1 is my top entry, my little k1, and my little k2 is negative 1 as my second entry. And that's my first eigenvector. That goes with my eigenvalue of negative 1. Now I would go through the same process, replacing the negative 1 with 4, and going through the same process will give me k2. I'm going to save us some time by not going through those steps here, but I'll tell you that what you'll end up with is K1 in this case is going to be 3/2 of K2. This is a time where choosing 1 is maybe not as nice because it doesn't end up with whole numbers. We end up with that fraction of 3/2. If instead I choose 2 as K2, then I end up with 3 as K1. So I'm going to do that so I get whole numbers. And now that I have my eigenvectors that go with my eigenvalues that I have, I can use our theorem and know that my solution is x equals C1, K1 is 1, negative 1, e to the lambda 1, so negative 1 times t, plus C2, K2, so 3, 2 in this case, e to the lambda 2, so 4, t. And that is my solution to my homogeneous system. Now, important to note here, I chose one that made it be negative 1 in my vector. If I had instead chosen 2, this equation would look different. It would be C1 2 negative 2 e to the negative t. And that's different, right? But what happens is those constants, C1 and C2, they're going to absorb the constant multiple difference. So it's really okay, and that's why that choice, you're allowed to make that choice, because the constants that we would solve for to find particular solutions would in fact absorb that choice. And so your choices that you make with the vectors will affect the outcome of what the constants would be. So it's possible that two people could solve this problem, come up with two different looking solutions that would in fact both be valid solutions. Sometimes when we look to find the eigenvalues, we actually end up finding that one of them shows up twice. If you think about it, when you solve a polynomial, sometimes a root is a repeated root. And since eigenvalues are in fact roots of the characteristic equation, then they can be repeated. And so let's take a look at an example where that's going to happen for us. So we're going to solve this differential equation I have here of x prime equals this beautiful matrix with 1's, 2's, and negative 2's in it times x. So the first thing we need to do is use our characteristic equation. So we're going to be taking the determinant of a minus lambda I. And for us, that's going to look like 1 minus lambda, negative 2, 2, negative 2, 1 minus lambda, negative 2, 2, negative 2, and 1 minus lambda. And we're going to be setting that equal to 0 just like we did last time. And we're going to solve that. This is going to end up telling us that we have negative lambda plus 1 squared times lambda minus 5 equals 0. That's after we've multiplied it out, we found our determinant, and we've then factored it. So what this is going to do is it's going to tell us, well, lambda 1 is going to equal lambda 2, and they're both going to be negative 1. And lambda 3 is sitting out here on its own. It's going to equal 5. So lambda 3 is probably obviously kind of the least of our worries because it's different than the other two, but the two that are the same, we need to figure out what to do with them. So before we said that if we took a times our eigenvector, it was going to equal our eigenvalue times our eigenvector. Another way of writing this is that a minus lambda times I, all multiplied times our eigenvector, must equal 0. And since our eigenvector, we don't want it to be 0, then we know that a minus lambda I must be 0. So we're going to do that. So if I have a minus lambda I equals 0, then I plug in negative 1 for lambda. So lambda equals negative 1 is going to make this turn into a plus I. And since I want it to equal 0, I want a plus I to equal 0, then I'm going to solve this. Now, plugging in lambda equals negative 1, I'm going to have that this is really a plus I times k is going to equal 0. So if I have a matrix times some vector of unknowns equals something and I want to solve this, we can do a thing called Gauss-Jordan elimination, and it allows us to solve. So the way we do this is we're going to set up a plus I. So our A matrix is again our coefficient matrix, so I have 1 plus 1. 1 in the A matrix plus the 1 that'll be in the I matrix on the main diagonal, so that'll be 2. And I have negative 2 plus 0, so negative 2, 2 plus 0, negative 2 plus 0. Remember, all we're doing is adding 1's down the main diagonal. That's what I is doing. So 1 plus 1 will be 2, negative 2 plus 0, 2 plus 0, negative 2 plus 0, and 1 plus 1 is 2. So we have this great matrix of all 2's and negative 2's now, and we want it to equal 0. So I'm going to put a vertical bar, and then we'll put some zeros that tell us what we want it to equal to. So that vertical bar is kind of like our equal sign now. So what we do is say, you know what? I want to turn this into an identity matrix the best that I can. And the first thing that I do is I notice, you know what? Row 1 and row 3, they're identical to one another. So if I just take row 1 minus row 3, and I put it back into row 3, it's just going to become a whole row of zeros. So I'm going to end up with 2, negative 2, 2, 0. And then the row 2 I didn't do anything to, so negative 2, 2, negative 2, 0. And then 0, 0, 0, 0. Well, and then I look at it and I say, you know what? Row 1, if I add it to row 2, it goes away too. So row 1 plus row 2, that's going to make another row of zeros and make my life real easy. So I'll have 2, negative 2, 2, 0 as my first row because I still didn't do anything to it. And I'll have zeros all the way across for the other rows. And then finally I look at it and I go, you know what, like 2's are great, but I really want those as simple as to look at as possible, so I'm going to multiply by 1/2 or divide by 2 depending on how you're thinking about it to make them 1s so they're even easier to work with. So we have 1, negative 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Alright, now remember I told you that the vertical line is like an equal sign, and remember that we were multiplying by our eigenvector all along here. So what this is really doing is it's telling me that I have k sub 1, lowercase k sub 1, minus k sub 2 plus k sub 3. My 3 entries in my eigenvector need to all add together to be 0. So I can solve for one of them in terms of the other. I could find that maybe I take k1 and realize that it really equals k2 minus k3. So that means I get to choose both k2 and k3, and from that I'll get k1. So if I choose k2 equals 1 and k3 equals 0, then that means that k1 will have to equal 1, because I'll have 1 minus 0 will equal 1. So there's a possibility. But remember, this all hinges on our choices that we make. I could have just as easily said, well, what if they're both 1? So I could have had k2 is equal to 1, k3 is equal to 1. Well, then I have 1 minus 1, so that means that k1 must equal 0. Well, looking at this, if I take these two vectors that I've made here, capital K1 we'll say one of them is, I have 1, 1, 0, and the other one's capital K2, and it's 0, 1, 1. Without even having to do any work to check, I know that these are linearly independent of one another because there's no way I can make a 0 turn into a 1 or a 1 turn into a 0. And since I have that situation, no linear combination or no multiple of one of these is going to create the other one. And so I have two linearly independent vectors that go with my repeated eigenvalue. When you have a repeated eigenvalue, this is what's going to happen. You're going to end up getting to make two choices, and as long as you make two choices that result in vectors that are linearly independent of one another, then you have done it perfectly. All right. Now, to find our third pairing, since we have a 3 by 3 matrix to work with and we had 3 eigenvalues, we're going to need all 3 for our final solution. So to find the last one, what we do is we'd end up plugging in 5 for our lambda value, so we'll be looking for a minus 5i times some k equals 0. In this case, it's k3. It's our third eigenvector that we're looking for. So to save us from having to write out all of these steps, I'll say we can go through and do the same thing. We can set it all up the same way. And when we do that, it's going to reduce down, and we're going to end up with something that looks like this. We'll end up with 1, 0, negative 1, 0, 1, 1, 0, and 0, 0, 0, 0. Now this is going to be what happens whenever you have an eigenvalue that's not repeated. You're going to end up with only one row of zeros. Now remember, these correspond to equations, so each row is going to give me an equation. I'm going to use m so we don't get confused here, and we'll have m1 minus m3 equals 0 from my first row. That's what it tells me. My second row tells me m2 plus m3 is going to equal 0. So now I can solve the first one and say, you know, this is really telling me m1 equals m3. And the second one, if I solve for m2, is going to tell me m2 equals negative m3. Now you'll notice here, I only get to choose a value for one of these things. If I choose one for m3, it's going to tell me immediately what m1 and m2 are. If I choose one for m1, it will tell me what m3 is, which will in turn tell me what m2 is, and the same if I choose m2. This is normal behavior when an eigenvalue is not repeated. So I'm going to go on and say, let's have m3 equal 1. That'll make m2. That'll make m2 equal negative 1. And it'll make m1 equal to 1. So that's giving me my third eigenvector. K3 is going to be 1, negative 1, 1. Again, we want to make sure that there's no way we could combine these. We want to check and make sure that they're linearly independent, that if they came from different eigenvectors, that if they came from different eigenvalues, that shouldn't be too much of a problem. So here we go. We've got our 3 eigenvectors to go with our eigenvalues, so we can go and put our general solution together. We know that x is going to equal, we take c1 times k1, so 1, 1, 0, times e to the lambda that went with k1 was negative 1, so negative lambda times t, negative t, plus c2 times 0, 1, 1, my k2, times e to its eigenvalue. Now remember, lambda 2 was also negative 1, so that's negative t as well. And then plus c3 times k3, 1, negative 1, 1, times e to that lambda, that eigenvalue that went with it was 5, so e to the 5t. And there we have our general solution when we had repeated eigenvalues. Now, since finding eigenvalues involves solving a polynomial, there's always a chance that we're going to end up with complex values for our eigenvalues. So when we have solutions that correspond to complex eigenvalues, we have a theorem to help us out with this. So A is going to be a coefficient matrix having real entries, and it comes from a homogeneous system. We're going to let K1 be an eigenvector corresponding to the complex eigenvalue lambda 1 equals alpha plus I beta, where alpha and beta are real. So basically we've got lambda 1 equals some complex number with a real part and an imaginary part. Either one of them can be 0, but not both. All right. So then we know that k1 equals e to the lambda 1t, and the conjugate of k1, e to the conjugate of our lambda or of our eigenvalue, times t are solutions. So let's take a look at what that looks like when we change it into real numbers, because we like working with real numbers more than keeping things in complex numbers. As much fun as it is to have conjugates of eigenvalues and vectors floating around. So a theorem about the real solutions corresponding to a complex eigenvalue. So we have lambda 1 equals to alpha plus I beta again. It's a complex eigenvalue, a coefficient matrix A, in a homogeneous system. And now we're going to define B1 and B2 to be the column vectors, where B1 equals this 1/2 of our k1 plus the conjugate of k1. What that really is doing is it's giving us the real part of k1. And b2 is negative I over 2 times negative k1 plus the conjugate of k1, which is really just giving us the imaginary part of k1. Then we have two real solutions that are linearly independent, x1 and x2, where we have b1 cosine of beta t minus b2 sine of beta t e to the alpha t as x1, and x2 being b2 cosine of beta t plus b1 sine of beta t e to the alpha t. So that might seem like a lot, so let's take a look at an example using these complex things, trying to find those real solutions for us. Alright, so we're going to take a look at this differential equation. It's an initial value problem, so I have my initial condition as a vector there given. And I need to first find our eigenvalues. So we're going to be taking our determinant of a minus lambda I and setting it equal to 0. So this is going to end up looking like 2 minus lambda, 8, negative 1, negative 2 minus lambda. Taking that determinant, setting it equal to 0, that determinant's going to end up looking like lambda squared plus 4 once we multiply everything out, simplify it. And so when we solve for lambda, we're going to end up with lambda equals plus or minus the square root of negative 4, which is going to give us plus or minus 2i. So what this is giving us is lambda 1 is going to be 2i, and lambda 2 is actually equal to the conjugate of lambda 1, and that's the negative 2i option. You can flip those around too. Doesn't matter which one's lambda 1 and which one's lambda 2. So then it's a matter of using our eigenvalues that we have here to find our eigenvectors. So when our eigenvalue is 2i, we're going to be looking at a minus 2i times the identity matrix times some k is going to equal to 0. So this is going to look like 2 minus 2i, 8, negative 1, and then negative 2 minus 2i times k1 to k2 equals 0, 0. And we can solve that, make it into a system of equations that we're going to be working with, and that system of equations ends up looking like 2 minus 2i times k1 plus 8k2 is going to equal 0. And negative 1 k1 plus negative 2 minus 2i times k2 is going to equal 0. So that second equation right now is the easy one to solve for just one of these. So that this tells me is that k1 is going to equal negative 2 minus 2i times k2. So if I choose anything for k2, that's my free choice that I get here. Then I find out what k1 is. So let's choose k2 equals negative 1. Get rid of some of those negative signs there for us. And we get k1 is going to equal positive 2 plus 2i. And so that tells me that k sub 1, capital K sub 1, is going to equal 2 plus 2i, and the second entry will be negative 1. And we can pull this apart and write it as a sum of vectors with a real and complex part too. So the real part is going to be the real numbers that don't have i's attached to them. So we've got 2 and negative 1 for that. And we're doing plus I times the things that have i's attached to them is a 2. And then there's no I in the second term, so the coefficient on I is 0. So what this has done in doing this is this right here is the real part of k1. And this part right here is the imaginary part of k1. So that's given me b1 and b2 to work with. So I don't actually have to find the eigenvector for my second eigenvalue since they're related, since they're conjugates of each other. I really just had to find the one so that I could pull it apart, get this real and complex part out, and then I can use my theorem to find my real solution. So I have x1 is going to equal b1. In this case, my b1 is 2, negative 1, that real part, times cosine of beta t. Beta is the part that goes with the I. Remember, we had alpha plus I beta. So beta in this case is 2. That's the part that's with the I in my eigenvector, or eigenvalue, sorry, right up there. So we've got 2 times t in our cosine minus b2. b2 is the imaginary one, so that's the 2, 0 vector. Sine beta is again still 2 times t. And we have e to the alpha t. Well, alpha is the part that doesn't go with the I in our eigenvalue. And the eigenvalue doesn't have a part without the I. It doesn't have a real part. So it's e to the 0. And that's just 1, so we don't even have to write that part. We get to go without it. And then that's our x1. Our x2 is going to be b2. Our 2, 0, that imaginary part of our eigenvector, paired with cosine of beta t, plus b1, so that real part, the 2, negative 1 part, paired with sine of beta t. And again, it's e to the alpha t, so it'll be e to the 0, which we don't have to write. And then, of course, when we have our two component solutions, to find our general solution, we have x equals c1 x1 plus c2 x2. And there we have it. That is our general solution. So now that we have this lovely solution worked out, it might be tempting to celebrate, but it would be a little bit premature. So remember, this was actually an initial value problem. I actually knew that x of 0 equals 2, negative 1. So we need to use that. and get rid of some of these constants in here. So in order to do that, I'm going to substitute 0 in for t, and then this 2, -1 vector goes in for our x. But substituting in for t while it's looking like this, it's difficult potentially. So let's write this all in one line. So we've got x equals c1 times x1. Now remember, x1 is this whole thing of 2, -1 cosine 2t minus 2, 0 sine of 2t, and c2 times x2, and x2 is this whole 2, 0 cosine 2t plus 2 times -1 sine of 2t. And that looks like a lot. So a common thing that we do is we go on and multiply and combine these vectors. So let's do that. So we've got c1 times what's going to end up being a single vector here. So we'll first take 2 as the coefficient on this cosine 2t, the top entry there. And then we're going to subtract from that the top entry again, 2, that's the coefficient on sine 2t this time. And then we're going to go to our bottom row of our vector. So we have -1 cosine 2t. And we have 0 times sine 2t. So that's the entirety there. So then we've got c2 times, again, it'll just be 1. We take our top coefficients and then our bottom coefficients. So we'll do 2 cosine 2t plus 2 sine 2t, and 0 cosine and plus -1, so minus sine 2t in our second entry. And now at this point I've done everything I can to make it as simple as possible to look at. It's never pretty. We're going to put zeros in for t, and we'll put 2, -1 in for x. So 2, -1 goes in as our x vector, and we have c1 still staying the same, and we'll be plugging 0 in everywhere we've got t's. So cosine of 2 times 0 is, cosine of 0 is 1, so this will be 2. Sine of 2 times 0 is 0, since sine of 0 is 0. So we don't have anything to worry about there. Cosine of 2 times 0 is cosine of 0, which is 1, so -1 is our second entry there. And then we have c2, and again we do the same thing. 0, 2 times 0 is 0, cosine of 0 is 1, 2 times 1 is 2. 2 times 0 is 0, sine of 0 is 0. 2 times 0 is 0, so we don't have to worry about that. And again, 2 times 0 is 0, sine of 0 is 0, so our second entry is 0 in this case. And now, we're still not done because we don't know what c1 and c2 are yet, but we have everything we need to know what they are. So I can write this, I can write everything on my right-hand side as a single vector now. So leaving the left-hand side as 2, -1, I have 2 times c1 plus 2 times c2, taking c1 times the first entry and c2 times the first entry in the second vector, and adding them together. And similarly, I do the same thing for the second entries, the bottom entries in the vectors. So I get -1 c1 plus 0 c2. And these need to equal the vector on the other side. So I get two equations out of this. I have 2 equals 2c1 plus 2c2 from the first entry. From the second entry, I get -1 on the left is going to equal -c1 on the right, and there's no c2 term. So this is easy enough to solve for c1. This is going to tell me that c1 is going to equal +1. And then I'll plug that into my second equation, my top equation, my first equation I guess it really is. That'll tell me that 2 equals 2 times 1 plus 2 times C1 times C2. And subtracting 2 across, I end up with 0 equals 2C2. And so this tells me that C2 equals 0. So now I plug in C1 and C2 back into the solution that I had. I'm going to go with this version, this cleanest version of the solution that we had to work with. So I'll plug it in. I have x equals C1 is 1, so just 1, I don't have to write it, 2 cosine of 2t minus 2 sine of 2t. And my second entry is negative 1 cosine of 2t. And then since C2 is 0, it zeroes out that second vector. So this is the entirety of my solution to my differential equation.